There's this hidden world of engineering that shapes the car you drive every single day. We're talking about pushing vehicles to their absolute limits long before a single piece of metal is ever actually cut. So let's dive into how engineers are using virtual physics to perfect our cars from the inside out.
I mean, it sounds a little like science fiction, doesn't it? How in the world can you know what's going to happen when a 2-ton vehicle plows through a wall of water without, actually doing it? Well, this is one of the toughest challenges in automotive design, and the solution is a complete game changer. To really get the solution, first, we've got to appreciate the problem. See, every car out there is in a constant battle with the forces of nature, especially the chaotic, totally unpredictable world of fluids. And we're not just talking about a little bit of rain here. Engineers have to design for deep water crossings that can literally rip parts off the bottom of a car. They have to manage the crazy, violent churning of oil inside a gearbox spinning at thousands of RPM. They have to stop snow from clogging up vital air intakes and safety sensors. All of it, these are powerful, destructive forces. For decades, the only way you could test for this stuff was to build a real prototype, drive it through a giant tub of water or into a blizzard, see what broke, and then go back to the drawing board. This whole cycle of build, break, repeat was incredibly slow, astronomically expensive, and honestly, sometimes just plain dangerous for the test drivers. There had to be a better way. And of course there was. A revolutionary approach that let engineers see these invisible forces with unbelievable clarity, all from the safety of a computer. Okay, so check this out. The old simulation methods used a fixed grid. It was kind of like trying to catch rain with a fishing net. You get a general idea, but you miss all the important details. The new way, the SPH way, completely throws that grid out the window. Instead, it tracks millions of individual digital particles, where each one represents a tiny little piece of the fluid. This method is called Smoothed Particle Hydrodynamics, or SPH for short. And that analogy is just perfect. Instead of just guessing where the floodwater is going, SPH simulates the actual physics of every single droplet as it hits the car and bounces off other droplets. This lets engineers see every splash, every spray, every churn with a realism that was just impossible before. So, with this powerful new tool in hand, engineers built the ultimate proving ground, a virtual torture chamber. Here, they could throw the most extreme conditions imaginable at their designs, over and over and over again. All right, let's start with a classic test, deep water wading. Driving through standing water seems simple enough, right? But for a car, it's packed with risks to its safety and reliability. When a car hits deep water at speed, the force can be absolutely immense. You could lose traction in an instant, water can get forced up into the engine's air intake, which is, well, it's catastrophic. But the biggest danger is often the one you can't see, the incredible hydraulic pressure that can bend parts of the frame or, as companies like GM found out in real-world tests, literally tear protective panels right off the underbody of the car. And this is where SPH is just so valuable. The simulations are now so ridiculously accurate that engineers at major car companies have found they can predict the exact location and the exact force that causes a part to fail. The virtual test now perfectly mirrors reality, which saves just a mind-boggling amount of time and money. Okay, let's move from the outside of the car to deep inside of it, to a challenge that's completely invisible but is absolutely critical for performance. Making sure oil gets to exactly where it needs to be inside a high-speed transmission or an EV motor. Think about it. At thousands of revolutions per minute, those gears are acting like a high-speed blender, just throwing oil everywhere. If the design's not perfect, you can get dry zones where metal is grinding against metal. Or you get the opposite problem. The gears waste a ton of energy just sloshing through too much oil. That's called churning loss. In an electric car, this can even cause critical electronics to overheat. So the billion-dollar question is, can the simulation actually predict this stuff accurately? Well, take a look at this. In direct comparisons with real-world lab data, the power loss predicted by the SPH simulation is nearly identical to what they actually measured. This gives engineers the confidence they need to tweak their designs for maximum efficiency, all on the computer. It's amazing. Now, here's where it gets really wild. The power of simulating all these little particles isn't just for water and oil. This technology has turned out to be incredibly versatile, helping to solve problems with materials you'd probably never even think of. Take snow, for instance. Is it a solid? Is it a fluid? Well, it's kind of both, right? SPH models can actually capture this really weird behavior. They treat snow as a plastoelastic material, which is a fancy way of saying it can pack together like a solid, but also flow and spray apart like a liquid. So why does this matter? Well, modern cars are just covered in sensors for safety systems, like automatic emergency braking. A virtual snowstorm can show engineers precisely where snow is going to build up and potentially block a crucial sensor or clog the engine's air supply, all before the car ever sees a single real snowflake. And the application goes even beyond how the car works in the wild. This exact same particle simulation tech is now being used to solve really tough challenges in high-tech manufacturing, specifically in building batteries for electric vehicles. Okay, so here's how it works. To keep batteries cool, a special thermal paste is put between the battery and a cooling plate. Now, if any tiny air bubbles get trapped when it's all pressed together, they create dangerous hotspots that can kill the battery's performance and its lifespan. So using SPH, engineers can simulate the whole process. The simulation shows them exactly where those tiny destructive air bubbles form, which lets them redesign the paste pattern to get a perfect bubble-free fit every single time. So when you put all of these pieces together, you start to see just how profound the impact of this technology really is. It's truly about making the invisible visible. The gains in speed and efficiency are just staggering. Get this, one case study found that a single physical test to see how snow built up on a car part took a full 30 minutes to set up and run. The equivalent virtual simulation, with the same accuracy, took just 30 seconds. That's not just an improvement, it's a complete transformation of how you develop a car. So what's the big takeaway here? SPH simulation turns incredibly complex, invisible physics into clear, simple data that you can actually use. This lets engineers build safer, tougher cars that can handle anything. It helps them design more efficient engines and motors that don't waste energy. And maybe most importantly, it just radically speeds up innovation because they can test thousands of what-if ideas in the time it used to take them to do one physical test. You know, it's funny. This all started with trying to understand the simple chaos of a splash. And now, that same understanding is optimizing everything from gearboxes to batteries. It really leaves you with a fascinating question. If we can now perfectly predict the behavior of millions of individual particles, what invisible challenge are we going to conquer next?